So in our analysis of the operational physics of a MOSFET transistor, we assumed that the steady state charges accumulated on the internal capacitances were acquired instantaneously, when in truth, we know that it takes time to charge and discharge a capacitor. So if we include that time dependence, our model will look something like this. So here's our gate terminal. And between our gate and our source terminals, instead of seeing simply an open circuit, we are now going to see a capacitor, CGS. Between our drain and source terminals, we are going to see GM VGS, where VGS is simply the voltage drop over CGS. If any body effects are present, we will have a second current source here, GMV VBS, and this will be in parallel with our channel length modulation resistance R naught. So a couple of other things here. Here's our source terminal, S. Here's our body terminal, B. Between the body and source, we can have a capacitance, CSB, over which a voltage, VBS, occurs. And we can also have a capacitance observed between the drain and the body, like so, where this will be CDB. Here is our drain terminal. And then finally, the thing that makes this extra annoying is a capacitance observed between the gate and the drain, called CGD. So this guy is pretty gnarly. However, there is a very common simplification that we will observe. If the source and the body terminals are wired together, we won't see any body effects present, which means this term goes away. And our capacitor CSB will be connected to the same node on both sides, so it goes away. So the overwhelming majority of the time, we're not going to have a contribution from this current source, and we're not going to have a contribution from this capacitor. In fact, unless I specifically state otherwise, we are going to work under the assumption that our source and body terminals are tied to each other, which means this capacitor CDB actually occurs between the drain and the source for the overwhelming majority of instances. So as we did with our BJT high frequency model, we're going to spend a little bit talking about where these capacitances come from. And to do that, we are again going to have to redraw our MOSFET model, specifically under saturation conditions. So let's say that this rectangular box here represents the bulk of our transistor. We are going to have a source region over here on the left. So this is an N+ region. And there will be a metal connection leading up to our source terminal. And just looking at this guy very specifically, we have an N+ region abutted next to a P-type substrate, which means we have a PN junction. And if our source terminal is ever at a higher potential than our substrate, we have a reverse bias junction. So getting a little bit ahead of ourselves here, we can see that we should have some capacitance CSB, which is going to be a junction capacitance, and it is largely going to be a reverse biased junction, so we'll treat it as some sort of depletion capacitance in a moment. On the opposite side of the transistor, we're going to have a similar configuration. This is our drain terminal. It's also N+ doped. We have N-type material right next to P-type material, so we have a PN junction, which will in turn have some capacitance due to the charge stored in the depletion region. This junction is also going to be reverse biased effectively all of the time. So we should see a junction capacitance based relationship here. All right. This pink region is representative of our polysilicon gate. And then finally on top, we're going to have our actual gate metal. Stop erasing things. Here's our gate terminal. Now, in an amplifier, our device is operating in the saturation region. On the saturation region, recall that we should have a channel and that the channel should be effectively pinched off. So something approximately like this, except imagine that I can draw a straight line. So we'll see a capacitance between our gate and our source, like so. We also have red. An area here, which I'm going to call LOV for overlap. We have one on both sides. So this one is also LOV. Now let's talk about that very briefly. Okay. The overlap of the polysilicon gate material over the N+ implants that form our source and our drain are a result of the fabrication process. Okay. So typically speaking, what happens is our polysilicon gate actually serves as a mask in a self-aligned gate process, which blocks ions from being implanted directly underneath the gate, right? So in old school processes, the source and the drain were patterned first, and then the aluminum actual metal was patterned for the gate itself. And there were alignment problems. Because if you didn't line things up exactly right, there was actually a physical gap between the gate material and the source and the drain material. The self-aligned gate process decided to do things in the other way around. You pattern the polysilicon first, and then you use the polysilicon as a mask to help you implant the source and the drain respectively. Well, after the source and the drain are applied or implanted, the wafer itself is heated up and it is annealed. And what that annealing process does is it effectively weakens the bond strength and allows a little bit of the drain implant to flow under the gate and a little bit of the source implant to flow under the gate as well. It's not a particularly large distance, typically on the order of 1/20th to 1/10th of the overall gate length underneath. So it's not big at all, but it is critically important to making the device operate correctly. So that overlap actually causes a small capacitance CGD, and there's one on the other side as well that we're going to lump into CGS momentarily. Okay. Finally, on the back side of the wafer, it actually isn't physically located here, but just for the sake of argument, we would have our body terminal. In truth, the body terminal would be implanted in a P+ region connected directly to the P substrate so that we would have an ohmic contact. There would not be a PN junction form there, so we wouldn't have to worry about another depletion capacitance or anything. Anywho, this is what our NPN transistor in the saturation mode looks like. These are where the parasitic capacitances come from. Now let's mathematically describe them briefly. Okay. So the gate source capacitance, CGS, arises because the polysilicon gate forms a parallel plate capacitor with the channel. When the channel is tapered and pinched off, the gate capacitance, CGS, is approximately equal to 2/3 the transistor width times the transistor length times the gate oxide capacitance per unit area, Cox. So that instead of it just being width times length times Cox, we have this other factor here because the plates are no longer explicitly parallel. Okay. We're going to add to this a term W L overlap Cox that represents the capacitance seen between the polysilicon gate and the actual source area here due to that region of overlap. Okay. At the gate drain interface, pinch off causes CGD, our gate drain capacitance, to be entirely based on an overlap. So that's just going to be WL overlap times Cox. Our source body capacitance, as mentioned previously, is due to charge stored in the depletion region of the source body junction. And so this is going to look like CSB naught divided by the square root of 1 plus VSB over V naught, where V naught here represents the built-in voltage of the source body junction. And finally, CDB is another depletion region capacitance. So it's going to look like CdB naught over the square root of 1 plus VdB over V naught. And in each case, these built-in voltages here, V naught for the source body junction and V naught for the drain body junction, they actually should be identical to each other because the drain and the source are identically doped with respect to the substrate. So those are literally the same built-in voltages there. Okay, so there's no need to differentiate them with their own subscripts. So these are the 4 high frequency capacitances. We can determine the unity gain or transit frequency of a MOSFET just like we did for BJTs a while back by simply short circuiting the drain and the source terminals. So we will develop a relationship for the transit time here. So let's consider this circuit. We have an input current. It's flowing into the gate terminal. And down here on the bottom, we're going to tie our source and body terminals together. So between the gate and the source, we see a capacitance CGS over which a voltage drop VGS occurs. Here we have GM, VGS in parallel with R naught, in parallel with CDB. Here's our drain terminal. This is again our source body, and we're going to short this guy out just like we did for our BJTs. Here is the current I out. The last thing that we need to do is attribute for this gate drain capacitance here. So arbitrarily calling this node Vx because that's what we did when we looked at the BJT case. If we apply Kirchhoff's current law at this node, the current flowing in is the current. So let's identify these guys real quick. So we have a current flowing in from the gate drain capacitance. We have a current flowing out due to this current source. And then we have this current flowing in where this guy right here is simply I out because the drain body capacitance in R naught would represent a path that the short circuit current would neglect, right? So our current flowing in is S CGD times VGS. So that's just the voltage VGS divided by the impedance of the gate drain capacitance. We're working in the Laplace frequency domain. So that's a current flowing in. The current I out also flows in, and a current of GM VGS flows out. We can rearrange this to find that I out is GM minus S CGD times VGS. Using Ohm's law, VGS is the current IN multiplied by the impedance of CGD in parallel with CGS, right? So we can say that these two guys are in parallel since our drain terminal is shorted out to our source terminal. So that's going to look like S CGS plus CGD, like so. And from here, we can get the short circuit current gain, I out divided by IN. So this is analogous to beta for a BJT. It will be a frequency dependent function. So if we substitute in our relationship for VGS into here, and then we divide both sides by IN, that's what we're getting. This is going to look like GM minus S CGD divided by S CGS plus CGD, or approximately GM over S CGS plus CGD. The magnitude of this gain approaches 1 at a frequency of omega t is equal to GM over CGS plus CGD, or approximately GM over CGS, since usually our gate source capacitance is much larger than our gate drain capacitance. The reason for this is because the gate drain capacitance is, again, a reverse bias junction capacitance, which means when our device is operating in saturation, that gate drain capacitance should be very, very small, intentionally so, right? From here, our transit frequency, or our ideal switching speed, whichever you want to call it, FT, is just GM over, that does not look like a 2 pi CGS plus CGD, or approximately GM over 2 pi CGS. So this is a figure of merit by which we compare MOSFET technologies. Okay, this is our transit speed, or effectively the fastest switching speed that we can achieve for a transistor biased in saturation. All right, so we have developed our high frequency models for both BJTs and MOSFETs. It is now time to Luke. So this is where our unity gain frequency for an amplifier would occur, at this specific frequency. Well, so this is where the short circuit, let me rephrase that. This is where the short circuit current gain goes to 1. All right. So we are now going to actually get into the frequency response of some of our amplifier circuits that we have analyzed. I am going to work specifically with MOSFET amplifiers, but the techniques that I'm showing you can be absolutely applied to BJT amplifiers as well. The principal difference there is that we're going to find that the Thevenin voltage and the Thevenin resistance equation are going to be slightly different because we have to include the contribution of R pi. But other than that, the derivations should be literally identical. Okay. So let's start with the frequency response of a common source amplifier. So we're literally starting with what your design project was, very much on purpose. Okay. We have some idea, at least I think most of us do, of how this circuit should behave as a function of frequency, because I literally asked you to tell me what it did. So let's start with low frequency analysis. And to that end, we are going to be analyzing this circuit. Here's R1. Here's R2. Here's our input capacitance Cn. We're going to include some potential signal resistance, R sig. This is where we're applying our input voltage Vn. Here is RS. Here's CS. Here's RD. And here's V out. So this should look extraordinarily familiar. The only fundamental differences here are that we are not loading our amplifier with a load resistance or anything in this case. Okay. So this circuit looks pretty terrifying to analyze with all of these capacitors in place. And I say all of these, there's a whopping 2. Okay. What we're going to do is we are going to apply linear circuit analysis techniques to make this circuit look like something much more familiar. So the first thing I'm going to do is I am going to disconnect effectively everything to the left of that dashed line, and we are going to replace it with its frequency domain Thevenin equivalent circuit. Okay. So recognizing that VDD is an AC ground, what we are doing is we're taking the following circuit where we have the in series with our sig in series with Cin connected to this network is R1, R2, like so. And we are going to try to find the Thevenin equivalent voltage, which I don't remember exactly what symbols we had been using for V Thevenin previously, because I know we've used it before. So I'm just going to write out V Thev because you can't mistake that for threshold voltage, thermal voltage, or anything like that. Sound reasonable? Okay. So how would we find the Thevenin equivalent voltage of this network? Let's start actually first by asking, does this representation look like everything to the left of the dashed red line? Let's start there, because if it doesn't, we are fundamentally in a little bit of trouble, because we're trying to replace everything to the left of the dashed red line with a Thevenin equivalent resistance, or a Thevenin equivalent circuit, excuse me. So do we agree about everything to the left of the red line looking like this at the small signal level?
Does VDD go away?
So VDD is a small signal ground because we're looking at the small signal behavior. So that's why R1 and R2 appear as if they are in parallel, because VDD is an AC ground. Any other questions, comments, concerns?
Why doesn't the capacitor not go away? It doesn't in the other stuff we were doing.
So fantastic question. So the reason why the capacitor doesn't go away is because we're specifically working at a frequency to where it's not a short circuit anymore. If it were a short circuit, we would no longer have a frequency dependence, right? So I want to jump at, oh, I don't want you guys to write this down, but I want to be very clear about what we're doing here, okay? So generically speaking, we know that this circuit, the frequency response of this circuit, so this would be the magnitude of AV as a function of S. It looks something like this, right? That's literally what your simulation should look like, okay? Where we're working right now is this area, the low frequency area, before our gain settles at a value of 7 dB, or a constant value for what we would expect from what we did in 335. So in 335, what we were doing was actually calculating quantities in the midband, where in the midband, the capacitors that we applied to the circuit to AC couple our input signal to the DC operating point were large enough so that they looked like short circuits, and the capacitors in our high frequency model were small enough so that they looked like open circuits, okay? So the analysis that we're doing right now is over here to the left, where our large capacitors that we are putting in don't quite look like short circuits yet. they're going to have some finite impedance. What we're going to be doing, my best guess would be on Wednesday, because we only have 30 minutes left of this class and we haven't even really started yet. We'll be working over here. In the high frequency range, where all of our internal capacitances of our transistors start to have an effect on the gain of our system. So is it clear the area that we're working in now? Okay. So let's circle back around. So that's why CN is no longer a short circuit. We're working in a range specifically where it's not yet short. All right, so I ask again, sincerely, does what I have drawn right here look like everything to the left of the dashed red line at a small signal level? Yes. Okay. So now we begin our analysis. How do I determine the Thevenin equivalent voltage here? Not a trick question. What other voltage source?
The V Thevenin is equal to Vn minus voltage drop over Cn.
You're doing too much work. There we go. It's a voltage divider circuit. It's the drop over these two in parallel. So we have an impedance here that is R sig in series with the impedance of SCN. So that's an impedance, let's call it Z1. This is an impedance Z2. So it's just Vn times Z2 over Z1 plus Z2. This is a voltage divider. Wonderful job. I'm glad somebody recognized it. All right. So using voltage division, V Thevenin is Vn times R1 in parallel with R2 divided by R sig in series with 1 over SCN, the impedance of our capacitor, plus R1 in parallel with R2. We're going to simplify this in just a moment. But does everybody agree that this is what our voltage division equation would give us? Okay. So all I'm going to do now is just multiply through by a factor of SCN over SCN to clear out the fraction in our denominator. Okay. This is exactly the same kind of crap that I was doing when I tried to teach you guys filters back in circuits 2. Literally the same thing. We're just treating it as a voltage divider and getting the transfer function of this stage. So this is going to look like Vn times SCN R1 in parallel with R2 divided by 1 plus SCN R sig plus R1 in parallel R2. How do we feel about that? Anything wild and or crazy? No. How are we going to get our Thevenin equivalent resistance or impedance in this case? We would be looking in through here with Vn turned off. I'm going to draw it out explicitly. But our Thevenin equivalent impedance, we need to be looking at a dead network, so that's why Vn is turned off. Here we have R sig. Here we have Cn. Here's R1. Here's R2. Here's our Thevenin impedance. What do we see? Yeah, R1 in parallel with R2 in parallel with a series combination of those guys. All right. So that's R sig plus 1 over SCN in parallel with R1 in parallel with R2. Okay. We've made everything to the left of that dashed red line look like a voltage source in series with an impedance. Okay. What we're going to look at now is everything that's left below this dashed blue line. So effectively, we're just trying to figure out what this degeneration stage looks like. It's just going to be an impedance, right? Because there's no voltage sources or anything like that that we need to concern ourselves with. And it's just going to be RS in parallel with the impedance of CS. So if this is our source terminal, here we have RS. Here we have CS. This is ground. I'm going to call this ZS, where ZS is RS multiplied by 1 over SCS over RS plus 1 over SCS. And if I multiply through by a factor of SCS over SCS, this gives me simply RS divided by 1 plus SCS RS. So that's my impedance seen effectively looking down from the source terminal of my transistor amplifier. So what we are going to do now is we're going to redraw our original circuit using these simplifications. So that's going to look like this. Here's VDD. Here's our resistance RD. Here's V out. Here's ZS, where I know I shouldn't just use the resistor symbol, but I'm trying to make it obvious that we've seen this before. Here's ZThev. Here's VThev. What is this? Something that we've done before. Absolutely correct.
Common source.
Common source amplifier with emitter, or excuse me, source to generation and
Source impedance.
a gate impedance. Yes. We know how it behaves, except now we have silly things like capacitances to worry about. They're built in, right? From an analysis perspective, we know how to treat this guy. So what I'm going to do, I'm going to call this node right here node X. We're going to say that our transfer function H of S, so this is our frequency dependent gain, output voltage as a function of frequency divided by the input voltage as a function of frequency. Literally the exact same crap we were doing back in circuits 2 when I tried to teach you guys filters. We can split this up into 2 stages, much like we did in 335. This is V out over Vx multiplied by Vx over Vn. Right? Okay. So actually, let's split this down into a third stage here because I've made a slight mistake because we no longer have a Vn in this picture. Instead of having a Vn, we have a Vthev, and so that's going to look like Vthev over Vn, like that. My apologies. But we already figured out effectively what that transfer function of Vthev over Vn is earlier, so we don't need to do any real work there. All right. So let's start with V out over Vx. How do we do that part? The correct answer is we go to our 335 notes and see what it is. And everywhere we had an RS, we replace it with a ZS. That is exactly what I'm looking for.
Negative RD divided by 1 over GM plus RS.
All right, so let me write that down over here in blue.
That is without in the
Yeah,
gate resistance, but it shouldn't matter.
it shouldn't matter because we're trying to find it between that gate thing and here. Okay, so read that out to me again, please.
Negative RD divided by 1 over GM plus RS.
All right. So what I'm going to do here, and I'll explain my logic briefly, is I'm going to multiply through by GM over GM. The obvious reason is because I don't want fractions inside of my fractions, but we'll talk about it again in a moment. So that's going to be GM RD divided by 1 plus GM RS. And then negative sign out front. Are we okay with that simplification? Okay. So all I'm going to do is I'm going to use this equation, which we derived back in 335, and I'm going to make the only change that I need to make, which is to replace RS with ZS. So V out over Vx looks like negative GM RD divided by 1 plus GM DS. Okay. So what's our transfer function? Vx over Vthev. It is exactly the number 1, 100% correct. And then lastly, we need our transfer function of VThev over Vn. So I'm just going to scroll up here. So if I take this expression right here and divide both sides by a factor of Vn, that's absolutely the transfer function that I'm looking for. So we're going to have SCN times R1 in parallel with R2 divided by 1 plus SCN R sig plus R1 in parallel with R2. And now it's just algebraic manipulation of things. Okay. So what I'm going to do here is I'm going to factor out this negative GM RD bit. This is important. Okay. This term negative GM RD represents the mid-band gain of our system, right? So this is effectively the gain of this circuit when our capacitors look like short circuits. Everything being multiplied by that is what's going to tell us how it behaves as a function of frequency. Okay, so it's very, very important that we are able to effectively pull out the mid-band gain and then multiply that mid-band gain by a frequency-dependent function, because this has to settle to the mid-band gain as the quantity S, our frequency, gets large, or as we approach the mid-band region. Okay. It has to.
Well, yeah, just looking at it mathematically, as S gets really large, that fraction is going to approach 1, which should equal just our regular gain.
Right. Let's get into that specifically. You're thinking about it correctly. You're absolutely thinking about it right. But we're going to break it down into a very specific form that tells us effectively where our poles and where our zeros are, so that we could draw a Bode plot of how this guy behaves, and it will literally exactly match what we simulated the other day. Okay. So I've pulled out my factor of negative GM RD. I'm going to multiply that by a factor of 1 over 1 plus GM. And now I'm simply substituting in the relationship that we got for ZS on the back, the last page, right? So I'm simply plugging this in and multiplying it by that GM. So it's going to be GM RS over 1 plus SCS RS and I'm going to multiply by SCN R1 in parallel with R2 divided by 1 plus SCN R sig plus R1 in parallel with R2, like so. And now what I'm going to do is I'm going to multiply by 1 plus SCS RS over 1 plus SCS RS to get this fraction out of the denominator of that first term. what that's going to give me is negative GM RD So let's work on the denominator first. So I'm going to have 1 plus GM RS plus SCS RS. Let's make sure that this bit makes sense. So all I'm doing is I'm taking the denominator of this first fractional term and multiplying through by that. So here I have 1 plus SCRS and then plus GMRS. I've grouped it together like this so that I have a real part and an imaginary part. Then I'm going to have 1 plus SCN R sig plus R1 in parallel with R2. In my numerator, I'm going to have that 1 plus SCS RS term. And then I'm going to have an SCN R1 in parallel with R2. So I should close this bracket here. My apologies. So I have my midband gain multiplied by a frequency dependent function. But my frequency dependent function here has been written in a very specific form because I can look at this guy right here and it will tell me where one of my zeros is. This contribution right here will tell me where another one of my zeros is. This contribution down here tells me where a pole is, and this contribution down here tells me where a pole is, so that I can reconstruct a Bode plot from this guy very, very easily. Okay. So that is our goal, to write our transfer function. Let me do this in blue. H of S in the form AM, where AM represents our midband gain, multiplied by FL of S, where FL of S represents the low frequency response terms, okay, which are all these guys up here. So this would be effectively AM times 1 plus S over omega Z1 times 1 plus S over omega Z2 all the way out to 1 plus S over omega Z sub n divided by 1 plus S over omega P1 times 1 plus S over omega P2 all the way out to 1 plus S over omega P sub n, which is the form effectively that we have. Or it's close enough to where we can figure out what our poles and zeros are by inspection. Okay. So from our transfer function, our amplifier has a pole omega P two at 1 plus GMRS divided by CSRS. It has a pole omega P1 at 1 over Cn R sig plus R1 in parallel with R2. It has a 0. R2 at one over CSRS, and it has a 0. Sorry. At a frequency of 0. So our pole frequency here comes from this guy. Our pole frequency here comes from this guy. Our 0 frequency here comes from this guy. Our 0 frequency here comes from this guy. And I've tried to, so one thing that we can't explicitly do here, so you might be arguing or asking yourself, well, why did you consider this omega P2 and this guy omega P1? From experience, the input capacitor is typically the largest capacitor, and so the pole associated with that input capacitance is usually going to be at a lower frequency than the pole that's contributed by the capacitor connected at the source function. So this is going to be, typically speaking, at a lower frequency, which is why it got a lower index. Same thing here. 0 is less than whatever this number is going to be. So that's why it got the 1 and this guy got the 2. So if we were to reconstruct our frequency response from this guy, what we would find is a graph that looks something like this. So here's omega. Let's call this omega P1. This will be omega Z2. This will be omega P2. And it should be increasing at 20 decibels per decade. Flatten out here. Increase again at 20 decibels per decade. Here, like so. Where this slope is 20 dB per decade. And this height corresponds to GMRD. And this height right here corresponds to GMRD over 1 plus GMRS. So effectively, we have a region here. That's why we have that hump, is because there's a series of intermediate frequencies in our frequency response where the impedance of our capacitor C sub S isn't quite 0. So that our degeneration resistor is contributing until we start making that capacitor look more and more and more like a short circuit, and then we settle to our actual mid-band gain. This looks strikingly similar to what you guys simulated. All right. That's enough out of me for today.